So today we are going to be talking about Thevenin and Norton equivalent circuits without dependent sources. Excuse me. And so in order to understand that, we are going to need to go over Thevenin's theorem as well as Norton's theorem. So let's start with Thevenin's theorem. Okay. So Thevenin's theorem states, excuse me, that any linear two-terminal electrical network can be replaced at the terminals by a voltage source VTH, which we're going to call our Thevenin voltage, in series with a resistance RTH, which is the Thevenin equivalent resistance. So effectively, what Thevenin's theorem tells us is that if we have a linear two-terminal network, we can replace it with a practical voltage source, because the Thevenin equivalent circuit contains only a voltage source VTH in series with some resistance RTH, which is exactly describing the practical voltage sources that we talked about in our last class meeting. So now let's talk about how to define that Thevenin voltage VTH and that Thevenin resistance RTH. So the Thevenin voltage VTH is the voltage drop measured across the open circuited terminals of the live network, where a live network simply means that our independent sources are on, and the Thevenin resistance RTH is the resistance seen looking into the open circuited terminals of the dead network, where a dead network is one in which all of our independent sources are turned off. Okay. As I said a while ago, today we're only going to be dealing with circuits that do not contain any dependent sources whatsoever. So there should be no opportunity for confusion here. Okay. Excuse me. All right, so I want to apply Thevenin's theorem to a circuit. And there are really two different ways that we can do this. Or actually, let me rephrase that. There are two different cases that we could possibly have, okay? So we could either be given an open circuited set of terminals to start with, which is arguably the easier case, but it's really not that different than the other thing. Or we could be asked to find the Thevenin equivalent circuit with respect to some particular circuit element, okay? And so I'll talk about the difference in the process for both of those. So let's put over here case number one. Thevenin equivalent circuit with respect to a resistor. Okay. So let's say that I have the following circuit. This is going to arbitrarily be an 8-volt source. Let's throw a 10 ohm resistor up here. 6 ohm resistor here. I'm going to put a 3-volt source here. Let's put a 15 ohm resistor. A 12 ohm resistor. And this will be a 20. Okay. And our ultimate goal in this case is going to be to determine the Thevenin equivalent circuit with respect to the 20 ohm resistor. And I'm going to tell us specifically here, assume the positive polarity terminal for finding VTH to be on top. Okay. So just so I don't have to redraw this thing, I'm going to make a copy of it really quickly here. So would you guys like to find the Thevenin equivalent voltage first or the Thevenin equivalent resistance? Voltage. Okay. So I'm just going to make a little note down here. So let's call this finding V Thevenin. And so what I'm going to do in this particular case is I have my circuit. Since I'm finding the Thevenin equivalent circuit with respect to the 20 ohm resistor, I can't allow the 20 ohm resistor to influence effectively the measurements that I'm taking. So I am going to remove it from the circuit entirely. And in doing so, I leave behind an open circuited set of terminals, right? So if I'm finding it with respect to a particular circuit element, I just take that circuit element out, okay? We are told in our problem statement to assume the positive polarity terminal for finding VTH to be on top. So here's my positive polarity terminal. Here's my negative polarity terminal. And our Thevenin voltage, by definition, is just the open circuit voltage across those terminals. Okay. So at this point, we could use literally any circuit analysis technique that we cared for in order to find this voltage VTH. So which circuit analysis technique would you guys care to use? So I hear some people saying nodal and some people saying mesh. So just for shits and giggles, let's do both and make sure that we get the same answer, okay? So using nodal, I'll do that over here on the left. I would need to identify my nodes. So here's one. Here's two. Here's three. Here's four. And here's five. So nodal seems like it might have been a not great choice, but we'll sort that out in a moment. Which node would you guys like to use as our reference node? Orange, the bottommost node would make the most sense to me because it's touching the most voltage sources. So that's going to actually make things significantly easier, right? So we don't have any dependent sources to worry about. So we don't have any controlling variable equations to write. So let me just assign nodal voltages here. So let's call this VA, VB, VC, and VD like so. And now we have two voltage relationship equations to write. So what's our voltage relationship equation for the 8-volt source? Yep, so 8 volts is equal to VA. What's our voltage relationship equation for the 3-volt source? VC is equal to 3 volts. Absolutely right. So applying KVL at our remaining non-reference nodes, so that would literally just be node B and node D, we would have VB minus VA, but we know that VA is 8 volts, so I'm just going to put this as VB minus 8 volts over 10 ohms, plus VB minus VC. We know that VC is 3 volts, so that's just going to be VB minus 3 volts over 6 ohms, plus VB minus VD over 15 ohms is equal to 0, right? So there are 1, 2, 3 currents leaving node VB. I have 3 terms. Everything seems okay. Applying KCL at node D, I'm just going to be adding this guy and this guy. So that looks like VD minus 3 volts over 12 ohms plus VD minus VB over 15 ohms is equal to 0. And now I effectively have a 2-equation, 2 unknown system that I can solve. So let's take a moment to do that. You guys want me to do it on a calculator on the board, or can I just throw it into my physical calculator real quick since we know how to do this by now? Let's go physical calculator. It'll be faster. All right, I guess I'll just use this one for today. So equation 2 simultaneous equations. So I just have 2 variables, VB and VD. So my coefficient for VB in my first equation is 1/10 plus 1/6 plus 1/15. My coefficient for VD in my first equation is negative 1/15. And my constant term is going to be 8/10 plus 3/6. In my second equation, my coefficient for VB is negative 1/15. My coefficient for VD is 1/12 plus 1/15. And my constant term is 3/12. Solving that system of equations, I find VB to be 381 over 82 volts, or 4.646 for those of you that don't like fractions. And VC, sorry, I'm mistaken there. VD is equal to 153 over 41, or 3.732. So before we move along from here, did anybody get different numbers when they solved that system? All right, so no one's saying anything, so either you didn't do it or you didn't get different numbers. Either way, we're moving along. All right, so now that we've solved for those nodal voltages, what is my Thevenin voltage for this system? So what's the nodal voltage at the positive polarity terminal of VTH? VD. What's the nodal voltage at the negative polarity terminal of VTH? 0. So VTH is simply VD minus 0. So we found that VTH is equal to VD, which is 3.732 volts. Okay. Making an assumption here that those numbers are correct. So let's throw nodal at this thing. Excuse me, mesh at this thing, because we've already done nodal. All right. So just reanalyzing the circuit just to verify our results and also to show you guys extra practice. Oop, oop. All right, so how many meshes should I have? I disagree. 2. So I feel like some of you guys, just to be really clear about this, I feel like all of you agree that this is a mesh, and all of you agree that this is a mesh. I very much disagree that this is a mesh because it isn't a closed path. So that mesh current IC would by definition be equal to 0. So it provides no information whatsoever. So if you want to call it a 3 equation, 3 unknown system, you go right ahead, but you already know that IC is 0. So why waste your time? Okay. So I'm going to erase that guy. Let's erase all this jazz down here because we're no longer doing nodal analysis and just see what shakes out. So we have identified our meshes. We have assigned our mesh currents. There are no controlling variables. There are no current sources. So all we have to do is apply our KCL equations here, right? So using mesh, we would have KCL around mesh A, which would look like -8 volts plus 10 ohms times IA plus 6 ohms times IA minus IB plus 3 volts is equal to 0. Applying Kirchhoff's voltage law around mesh B, we would have 6 ohms times IB minus IA plus 15 ohms IB plus 12 ohms IB is equal to 0. Once again, 2 equation, 2 unknown systems, so we can solve this for IA and IB. So let me do just that. So in my first equation, my coefficient for IA is 10 plus 6, so that's 16. I can just do that one in my head. My coefficient for IB is -6. And my constant term is going to be +8 minus 3, so that's 5 to me. In my second equation, my coefficient for IA is -6. My coefficient for IB is 6 plus 15 plus 12. And my constant term is 0. Solving this, I get IA to be 55 over 164. And IB to be 5 over 82. Now that we know these mesh currents, how might we go about solving for VTH? So this is effectively where we're going to apply Kirchhoff's voltage law to that third, not really a mesh, because now that we know what our currents are, we know the voltage drop across every resistor just by applying Ohm's law, so we can write KVL around that bottom right-hand loop in order to figure out what VTH is. So applying KVL down there, so KVL at bottom right-hand loop, we would have -3 volts plus, so actually, minus 12 ohms times IB. So just to be clear, IB is effectively flowing into the positive polarity terminal. So when we do KVL, we would have negative 3 volts, negative 12 ohms times IB, and then plus VTH is equal to 0, which tells us that our Thevenin voltage is 3 volts plus 12 ohms times IB. So 3 plus 12 times 5/82. Screw you, syntax error. 3 plus 12 times 5/82 gives me 153/41, or 3.732 volts. So it seems to me like we got the same answer using nodal or mesh, which we should, just to be real clear. They should never be different. Okay. So in order to, let's just recap things really quickly, okay? So we were finding the Thevenin equivalent voltage with respect to a particular circuit element. So what we did is we took that circuit element out, and then we just solve for the open circuit voltage using whatever the hell circuit analysis technique feels right to us. It does not matter what technique we use. Anything that gets us the correct answer is a perfectly valid thing, right? So we can use nodal, we can use mesh, we can use Ohm's law, KVL, KCL, voltage division, current division, superposition, whatever the hell we feel like, as long as it gets us VTH correctly, whatever works. Yes, sir. So Kirchhoff's voltage law is the says the sum of the voltage drops around any closed path is equal to 0. Who cares about current? If I have defined voltage drops, I'm good to go. So imagine, if you will, we had this circuit and we were applying our multimeter to these terminals. We just did what our multimeter does. Just finding the potential difference between 2 points in the circuit. Okay. So KVL, if we have well-defined voltage drops, we can apply KVL. KCL is the one that has anything to do with currents. All right. So how are you guys with this? Yes, Maddox. Which resistor? The one we took out? So they're going to wind up being significantly different voltage drops. And I'll prove that here in just a couple of minutes, okay? So it shouldn't be difficult to understand that they should have a different value of voltage, because our circuit analysis would be significantly different if that 20 ohm resistor were actually in the circuit, right? So when we applied our mesh analysis, we would have had a third closed mesh and dealing with a mesh current that is not 0. When we applied our nodal analysis, our Kirchhoff's current law equation at node D would have had an extra term. So it would have resulted in a significantly different value for that voltage, okay? So what we're doing is we're finding this open circuit voltage, and then we're going to use that voltage along with the Thevenin resistance to construct an electrically equivalent circuit that will make calculations easy, if we're interested in things like power and all of that kind of good stuff, okay? But this can also be used as a circuit analysis tool. Just for the sake of argument, if I have a complicated network that I can disconnect and leave behind a 2-terminal network, I can just find the Thevenin equivalent of that thing and use that to represent the big ugly thing I don't want to deal with. So anyway, we do that a whole hell of a lot in higher level electrical engineering classes, and this class will do it every now and then. But anyway, all right, so finding RTH. So I'm taking my original circuit. Since I'm finding the Thevenin equivalent with respect to the 20 ohm resistor, I am once again just going to take the 20 ohm resistor out of the circuit. Okay. The Thevenin equivalent resistance is always found by looking into the terminals of a dead network. I have two voltage sources that are on, so I do not currently have a dead network. How do I turn voltage sources off? Replace it with a short circuit. So my 3-volt source is a short circuit. My 8-volt source is a short circuit. And now this is literally just a resistor combination problem. Okay. So let's identify our nodes, and I hope I didn't accidentally give us a circuit that's going to require a delta or Y transformation, and if I did, we'll get around that. So there's one node. Here's a second node. And here is my third node. I'm going to call this node A, B, and that makes this guy up here C. So I'm going to put A on the left-hand side and B on the right-hand side. So to go from A to B directly, I have that 12 ohm resistor. I could also go from A to C to B. So let's put C right here. So to go from A to C is through the 15 ohm resistor. And then to go from C to B is either the 10 or the 6. And so, okay, I don't have to do anything fancy here. So 10 and 6 in parallel is 60 over 16. 60 over 16 plus 15. So let's see, 60 over 16 plus 15 is 75 over 4. That's in parallel with the 12. So I'm just going to do answer times 12 divided by answer plus 12. And I get a resistance of 300 over 41 ohms. Anybody cares to throw that in their calculator and verify I didn't make a mistake? Go nuts. So now to circle back around to Maddox's question, what we have done is we have found a Thevenin equivalent circuit with respect to that 20 ohm resistor. So let me just call this putting it all together. So our original circuit is, as it turns out, electrically equivalent from the perspective of the 20 ohm resistor to this circuit, where we would have a 3.732 volt source in series with a 300 over 41 ohm resistance. And then this is our 20 ohm resistor. So we can replace all of that big ugly network that was connected to the 20 ohm resistor by literally a practical voltage source using this method. So for what it's worth, the source transformation thing that we learned in our last class meeting is effectively pointless now. Because instead of flip-flopping back and forth between different forms to get things, either a practical voltage or let's start with a practical voltage source connected to an arbitrary load resistance, we can now replace that with find the Thevenin equivalent with respect to the load resistance, and we wind up with the exact same result, but we have a lot more freedom in how we get to that end result, right? So on your exam on Monday night, you are not specifically being tested on Thevenin equivalent circuits in any way, shape, or form. However, you can definitely use this technique for those problems on source transformation to get the same result. It may be quicker, it may not be, it just depends on how much of an ass I am when I'm creating the circuits. Ella.
Is going to be replaced with that one we just found.
Yep. Absolutely. So let's talk about where a Thevenin equivalent circuit would be used in practice, okay? Because as far as an analysis tool, it can have its uses. Like I said, if you have something particularly complicated that you can make look like a two-terminal network by disconnecting it, you can just find the Thevenin equivalent and plug that back in. Okay. If we wanted to know, let's say we were designing a piece of electronic equipment, and we needed to know whether or not our load was going to be supplied with so much power that it could likely burn out or something. Instead of analyzing our circuitry, we would just find the Thevenin equivalent with respect to our load. That would give us an easy way to calculate our power, because I feel like analyzing this circuit is incredibly trivial. And by the way, we wouldn't mathematically determine our Thevenin equivalent circuit, we would just measure it, right? So if we have our voltage sources on and we measure the open circuit voltage, that is us measuring our Thevenin voltage. If we turn our voltage source off or whatever and measure the resistance seen looking into those terminals, that gives us our Thevenin equivalent resistance. And from that, we can just construct this circuit to do a very simple power analysis and find out, hey, am I going to burn this thing out or not? So very, very useful tool used in industry all the time, particularly in troubleshooting and things like that. Okay. Okay, so the other case would be finding the Thevenin equivalent or circuit with respect to a set of terminals. So how do you guys think that that would be different? There's no element to take out because we already have an open circuited set of terminals to deal with. That's literally it. So I might give you something like this. So let's say that I have the following circuit. And just to make this goofy and annoying, I'm going to put terminal A here. And terminal B down here. I'm going to move, I'll leave it there. All right. So this is our circuit that we're finding the Thevenin equivalent with respect to now, right? So once again, I'm just going to find VTH by whatever means seems appropriate. So let me just make a copy of this. So my Thevenin equivalent voltage, I'm just moving this 2 amps over so it's easier. Oh, and let's say, just for the sake of argument, that I'm going to put positive polarity on top, negative polarity on, or positive polarity at A, negative polarity at B. When I give you a homework assignment or an exam question or anything, I will always explicitly tell you which one to assume for the positive polarity terminal. Okay. So there was no particular rhyme nor reason for me choosing positive polarity at A, negative polarity at B, but we'll get to that. All right, so there's our Thevenin voltage. It's just the voltage measured between terminals A and B. So how would you guys care to solve for it? Mesh, okay? So using mesh, let's call this IA. This IB. So our meshes are identified, our mesh currents are assigned. There is no dependent sources, so we have a current source. So what's our current relationship equation going to be? 2 amps is equal to IA minus IB. Now we would write a KVL equation around our super mesh, so just around the perimeter of our circuit. So that would look like negative 6 volts plus 8 ohms times IA plus 5 plus 12 is just 17 ohms. So 17 ohms IB is equal to 0, and we can solve this system. So I will do that real quick. So in my first equation, my coefficient for IA is 1. My coefficient for IB is -1. My constant term is 2. In my second equation, my coefficient for IA is +8. My coefficient for IB is +17. And my constant term is +6. Solving that, I get IA is 8/5 of an amp, and IB is -2/5 of an amp. So how would I find VTH now? So I think I could do KVL around this path, effectively telling me that VTH is just going to be 17 ohms times IB. So 17 times -2/5 would be -34/5, excuse me, volts. Any questions about any of our analysis there? Okay. So now I would need to find RTH. So once again, I'm just going to start from my original circuit. Since I have a set of terminals already, I don't need to take anything out, so I'm good to go there. So I just need to turn things off. So my 6-volt source becomes a short circuit. My 2 amp source becomes an open circuit. And so my resistance is seen looking between terminals A and B. So what do I see? 8 in parallel with 17. Anybody got a beef with 8 in parallel with 17? Hopefully we can just look at this one and sort that out. So 8 ohms in parallel with 17 ohms. So that would be 8 times 17 divided by 25 is 136/25. Oops. So our original circuit would be electrically equivalent to this guy right here, where that is 34/5 of a volt in series with 136/25 ohms. I got rid of my negative sign by flipping the polarity of my voltage source. So how comfortable do you guys feel with this? I even hesitate to call it a process at this point, right? So finding the Thevenin equivalent voltage is just applying whatever circuit analysis technique allows us to find the voltage drop across that open circuit. For what it's worth, a lot of you guys seem to want to just throw mesh at it. There's nothing particularly wrong with that, but I would argue that if we're finding a voltage, nodal might be a little easier so that we wouldn't have to come up with these weird KVL loops at the end, but whatever floats your boat. And then finding the Thevenin equivalent resistance is, for these particular circuits with no dependent sources, just a resistor combination problem, right? All right, so now let's look at Norton's theorem. So it is amusing to me. So Thevenin's theorem was come up with, I think, in the 1880s. I may be misremembering my dates here, and it's not particularly important, except to say that Norton's theorem didn't become a thing until the 1920s. Okay. So Norton's theorem states that any linear two-terminal electrical network can be replaced at the terminals by a current source, I Norton or INO, in parallel with a resistance RNO. So Norton's theorem says any linear two-terminal electrical network can be replaced by a practical current source. So it amuses me that it took 40 years of electrical circuit theory for people to go like, hey, if we can make this thing look like a practical voltage source, we could probably make it look like a practical current source too. Anywho, so let's define how to determine our Norton current and our Norton resistance, okay? So the Norton current I Norton is the short circuit current flowing between the terminals of the live network. So effectively, let's talk about this very briefly. For our first case, where we were finding an equivalent circuit with respect to a particular element, when we were finding the Thevenin equivalent voltage or the Thevenin equivalent circuit, we took that element out and we left those terminals open circuited. When we're finding the Norton equivalent current, at least, we take that element out and replace it with a wire. So we just short those terminals out and then find the current that's flowing through the short, and that is by definition our Norton current. Okay. The Norton resistance is the resistance seen looking into the terminals of the, dead network. So the definition for the Norton resistance and the Thevenin resistance are literally exactly the same thing. So you will never hear me refer to Norton resistance again. I will always just call it Thevenin resistance, okay? So let's go back to our first case, and I'm going to be lazy and I'm just going to copy this circuit. Select. So here's my original circuit. We are going to find the Norton equivalent circuit with respect to the 20 ohm resistor. And we are going to assume that the reference direction for determining I Norton is down. So I want to be very clear about this choice. Okay, actually, this choice with respect to what we did for the Thevenin, finding the Thevenin equivalent, finding the Thevenin voltage. So the Norton current should always be leaving the positive polarity terminal of the way we found the Thevenin voltage. So if we defined VTH with the positive polarity on top, then our Norton current should be down. If we defined VTH when we were finding it as positive polarity on bottom, then our Norton current should be up. If we define VTH when we're finding it as positive polarity on the left, then the Norton current should be flowing to the right. Okay, so just to be clear. Like I said, I will always tell you what reference direction you should have and which reference polarity you should have. But if you're ever attempting this on your own, if you make the wrong choice, what you'll find out when we learn something else here in just a couple of minutes is that you might think your Thevenin equivalent resistance is negative, which can't happen. So it just means you chose one polarity backwards or the direction for the current backwards. Not a big deal. Just making you aware of it. Okay. So let's find I Norton. So I'm going to take my circuit. I take my 20 ohm resistor out and I replace it with a short. My Norton current is simply the current flowing through the short circuit. So how might we find this current? So this is like the one time where I actually feel that mesh is appropriate. I'm trying to decide whether or not to be an asshole and just use nodal anyway, just because I can. Let's use mesh. That would be the thing that I think most of you would lean towards here, right? So we could have a mesh current IA here on the left-hand side, a mesh current IB up here on the top right, and a mesh current IC down here on the bottom right. So let's see, we've covered steps 1 and 2 because our meshes are identified and our mesh currents have been assigned. We don't have any controlling variables. We also don't have any current sources. So I think we're just good to write KVL equations. So that would look like -8 plus 10 ohms times IA plus 6 ohms times IA minus IB plus 3 volts is equal to 0 for mesh A. For mesh B, we would have 6 ohms times IB minus IA plus 15 ohms IB plus 12 ohms IB minus IC is equal to 0. And then around mesh C, we would have negative 3 volts plus 12 ohms IC minus IB is equal to 0. And so we have a 3 equation, 3 unknown system. So let's solve for IA, IB, and IC real quick. Shit. All right, so in my first equation, my coefficient for IA is 16. My coefficient for IB is -6. My coefficient for IC is 0. And my constant term is +5. In my second equation, my coefficient for IA is -6. My coefficient for IB is 33. My coefficient for IC is -12. My constant term is 0. And my third equation, my coefficient for IA is 0. My coefficient for IB is -12. My coefficient for IC is +12. My constant term is +3. And in solving this system of equations, I get 41 over 100 amps, 13 over 50 amps, and 51 over 100 amps. How would I express my Norton current in terms of those mesh currents? Just IC. So 51 over 100 amps. Okay, so there is a way for us to verify if we are correct, okay? So I want to think about things contextually here, okay? So we just found the file, no, paste, okay. So this was our original circuit, okay? When we did the Thevenin equivalent circuit, we found that our original circuit was the same as this 3.723, if I'm remembering that voltage correctly, and if I'm not, please correct me, in series with some resistance that I'll scroll up for in just a moment, connected to a 20 ohm resistor. 732, and then that is 300 over 41. Sorry for transposing those, and then 300 over 41 ohms. And when we did our Norton analysis, we just found that this thing is also electrically equivalent to a 51 over 100 amp current source connected in parallel to that same 300 over 41 ohm resistor, because the Norton resistance and the Thevenin resistance are literally the same thing. So I didn't bother doing it again because we already knew what it was. And this is connected in parallel to our 20 ohm resistor. So based on what we have here and what we learned in class on Wednesday, it should be fairly obvious that since the Thevenin equivalent circuit is electrically equivalent to the thing on the left, and the Norton equivalent circuit is electrically equivalent to the thing on the left, then the Thevenin equivalent circuit must be electrically equivalent to the Norton equivalent circuit. They are just source transformations of each other. 40 years. So that means we can verify our answers inherently, right? So we know fundamentally that because we know how source transformations work, that now our Thevenin equivalent voltage should be the same thing as our Norton current multiplied by our Thevenin voltage, or our Norton current is just Thevenin voltage divided by Thevenin resistance, or Thevenin resistance is just Thevenin voltage over Norton current. So technically speaking, we can either use 2 to find the other quantity, or we can determine all 3 and then make sure that checks out. And if it does, we know that we did everything correctly. Okay. So just for the sake of argument here, I'm going to take this 51 over 100. I'm going to multiply it by 300 over 41. So 51 over 100. Multiplying that by 300 over 41. And I get 153 over 41 volts, which is 3.732 volts. So we must have done everything correctly, because if we didn't, that wouldn't have come out that way. Do I need to walk you through finding the Norton current for the second case? All we're going to do is connect those 2 terminals with a short circuit and then find the current flowing through the short. All right, so I'm done ranting at you guys for today. All right, so let's discuss a couple of things really quickly with regards to the test. It's Monday at 6 for the overwhelming majority of you. I say the overwhelming majority of you because I believe there are 3 students who are currently enrolled in a project management course that meets on Mondays at the same time. So I have to find something that accommodates them. But if you don't have a conflicting class, your test is on Monday. Just to be real clear about it, you don't get to pick and choose shit. It's on Monday. It's been on the syllabus since the first day of class. I have the location of the exam in my email somewhere. I will post that to Canvas today to let you guys know where you're supposed to go and all of that kind of good stuff. Since our exam is on Monday, we do not officially have class on Monday because the exam counts as our class meeting. However, I will be here for a completely optional review session if you care to come in and ask any questions or anything like that. How my review sessions work is you bring questions, I answer them. As soon as you stop asking me questions, I leave, because our class meeting is at the night, so I am not being paid to be here at 8 o'clock in the morning on Monday. I'm just doing it out of the kindness of my jackass heart, okay? So if you don't come in with any questions, I will happily go in my office and play video games for that 2 hours or whatever, okay? Probably should be doing work. I know me, I'm gonna play video games if you let me do it. So anyway, so that's what our plan is for Monday. So Monday morning, optional review session, not taking attendance. Anybody that wants to come in, come in. If you think you got it, that's great. I've got no comment beyond that yet. We'll see what your grades say. Exam is Monday evening at 6 p.m. somewhere here in this building. As soon as I find that email, I'll let you know where that somewhere is. All right, in-class assignment stuff.